This video describes the process of sizing linear and PWM amplifiers driving a rotary brushless motor and uses a simple Excel spreadsheet available at the Viridin website. A typical motion control system is represented by this block diagram. There's a motion controller that specifies an angle profile theta of t, which implicitly defines an angular velocity profile. This motion is assumed to be periodic, that is, once completed, the motion repeats itself. We use the velocity profile in the amplifier sizing process. There is a Viridin linear or PWM amplifier that commands 3 phase currents, which in turn drive the rotary brushless motor and load. Our goal is to determine the amplifier requirements given the velocity profile and the motor and load parameters. The needed motor and load parameters are the motor torque constant, often expressed in Newton meters per amp RMS, the motor phase-to-phase back EMF constant, which we express in volts peak phase-to-phase per radian per second, the phase-to-phase resistance R, inductance L, and the number of motor poles N. Also the motor load inertia J, which includes mass or inertia inside the motor and inertia outside the motor, expressed in kilograms meter squared, for example. With these parameters and the angular velocity profile, we can specify these 5 amplifier requirements. They're the amplifier bus voltages, which are bipolar plus minus B for a linear amplifier and unipolar at 2B for a PWM amplifier. So the PWM has a single supply with a ground return. In both cases, the rail-to-rail voltage is 2B. There's a peak output current, I peak, and the continuous output current, I continuous. For PWM amplifiers, these 2 current requirements allow us to compute output transistor power requirements as well. For a linear amplifier, we need separate calculations, and those are the peak output power and the continuous power dissipation. Those 2 quantities are marked with an asterisk to indicate that the calculations that we use are for linear amplifiers only. In the case of PWM amplifiers, the power spec is rolled into the current specs, and that's what you'll see on the data sheet. Let's do an example. Here are our motor parameters. We're choosing the torque constant to be 1.23 Newton meters per amp, the back EMF constant 1.0 volts peak per radian per second. The phase-to-phase resistance is 1.5 ohms. The phase-to-phase inductance is 23 millihenries. The number of poles is 20. And the total rotary inertia is 0.05 kilograms meters squared. The angular velocity profile we're using is a trapezoidal motion. This is what we ask for as input to our spreadsheet. The nice thing about a trapezoidal profile is we can specify it with these 9 corner points. So we input into the spreadsheet 0 seconds and 0 RPM, 50 milliseconds and 200 RPM, 450 milliseconds and 200 RPM, and so forth, all the way up to 1800 milliseconds and 0 RPM. Here's the spreadsheet for sizing linear and PWM amplifiers driving a rotary brushless motor. The spreadsheet is color-coded. The blue indicates design inputs and the green indicates design outputs. Specifically, in these bolded cells, we input the motor parameters, various units. Here again, for the trapezoidal velocity profile, we put in the corner points and the units. For example, for the torque constant, we have 1.23 Newton meters per amp RMS, as we saw in the previous slide, and we can change the units amongst these here. For the back EMF constant, we have 1 volt per radian per second, and there's also some unit selections that we can make here. Ohms are the units for the phase-to-phase resistance. Henries are the units for the phase-to-phase inductance. We had 23 millihenries, so we converted to henries here. The number of poles is 20, and we have some unit options for the inertia as well. For the angular velocity profile, we specify that in RPM. Sometimes we use radians per second or others. And the corner times are 0 seconds, 0.05 seconds, equivalently 50 milliseconds, 450 milliseconds on up to 1.8 seconds. And the corner velocities are 0 RPM, 200 RPM, 200 RPM, 0, 0, minus 200, 0, 0, so forth. And the spreadsheet computes the bus voltages, the peak and continuous power, and the peak and continuous current. For a linear amplifier, the bus voltages are plus minus B, where B is given here at 78.4 volts. For a PWM amplifier, the bus voltage is, the single bus voltage is 2B, okay, so 2 times 78.4 volts. And we can include margins on these various specifications if there's some uncertainty in our estimates. For example, if we knew that our power supply voltage wouldn't suffer any dips or variations, and that our trapezoidal profile is indeed exactly our worst case, we could set that margin to 0 and run things at a bus voltage of plus minus 65.4 volts in the case of a linear amplifier. We usually use a 20% margin on the bus voltage. Now the peak output power, that applies to linear amplifiers only. Okay, likewise, again, marked with an asterisk. Likewise, the continuous power is marked with an asterisk, and that applies to linear amplifiers only. iPeak and iContinuous apply to both linear and PWM amplifiers. So that's it. Input the numbers. The calculation is automatic. Just email this to sales@veredin.com, and we can help you select an amplifier.